So today we shall start with third unit, that is ARM instruction set. So this is the third unit of your syllabus where we'll be discussing the instructions supported in ARM state. So all the 32-bit instructions we are going to discuss in this unit. Okay. And you know that ARM instructions, they process the data held in registers and they are going to access the memory only with load and store instructions. So data processing operations are performed on only registers since ARM uses load store architecture. So ARM will not make use of that is the memory for data processing operations. Only through load and store instructions we can access the memory. So don't go for using this memory operand in arithmetic instructions or move instructions or logical instructions. So only for load and store mnemonics you can make use of that is the memory operand. Okay. So coming to the instruction format ARM uses. So it uses commonly 2 or 3 operands in an instruction. You can see this template. So this is the instruction syntax. That is an example is considered here. Add R3 comma R1 comma R2, where add is the mnemonic or the opcode. R3 is the destination register RD, and R1 it is the source register 1, and R2 is the source register 2. So in general, we'll be using these registers. RD, that is the opcode will specify, followed by that RD comma RN comma RM. In our example, we have taken add R3 comma R1 comma R2. So what this instruction will do, it adds the 2 values which are stored in the registers R1 and R2 and it stores the result, or it writes the result to R3 register. So this is the format used in the instruction set of ARM. Okay, it uses 2 or 3 operands, and this is what the syntax. First operand is the destination operand, followed by that we are going to specify the source operand, which may be one source operand or 2 source operands, and in general they are named as Rn and Rm. Okay, Rn is the source register 1, Rm is the source register 2. Okay. Coming to the examples that are used in your prescribed textbook, this is what the same format that is followed. Okay. We are going to specify the preconditions, that is before execution of the set of instructions. What are the status of the registers, or if any flags are being affected, what are the status of the flags? All those will be recorded before execution. And we are going to write the instructions, sequence of instructions. After that, we are going to specify the post conditions. So after execution of the instruction, what will be the effect on the registers and flags? We are going to record. So the same template is being used for explaining all the examples in your prescribed textbook. So this is the format being followed. Precondition, then followed by that instructions, then after that we're going to specify the post conditions. Okay. So if it were to be memory, in your instruction, if memory is being referred, so in case of pre and post conditions, this is how the memory is denoted. Okay. Mem is used. After that, some data size is specified, whether it is the 32-bit data or 16-bit data or 8-bit data being handled. And within square braces, we are going to specify the address. So how many bit data being read or written at which address? The starting address is specified within square braces. So that's what we'll explain here. This refers to the data size, okay, of the memory starting at the given byte address. Say for example, if you consider the template as mem32 of 1024, so what it means is 32-bit value starting at address 1024. So that is the meaning. So 32 indicates the data size and the starting address is indicated with a square brace. So as and when we use this template in our examples, you'll better understand. Okay, for the timing, just know that whatever the examples we are going to discuss from now on, we'll be using this template where before writing the sequence of instructions, we'll specify the preconditions, and after the instructions, we'll specify the post conditions. Okay. Now we shall look into the instruction classes of ARM. So there are different instruction classes supported in ARM. So this is how the instruction class is classified. Okay, first is the data processing instructions, then comes the branch instructions, then load and store instructions, software interrupt instructions, program status register instructions. Okay, if we complete these instructions, actually we'll be completing with unit 3. So this is how the instruction classes of ARM are classified: data processing, branch instruction, load store, software interrupt instruction, program status register instructions. So in turn, data processing instructions are classified into different instructions. So what are those? We'll be looking into that in the next slide. So branch instructions, we'll be discussing conditional and unconditional branch instructions, how we can write. And with respect to load store instructions, we'll be discussing how to load to a single register transfer and multiple register transfers we'll be discussing. That is loading a single value from the memory and transferring it into a register, or writing a single value held in a register to the memory, or it may be multiple registers you may have to deal with. So load multiple and store multiple instructions. All these different types of load store instructions and the addressing modes which you can use with respect to load store instructions. So all these things we'll be discussing once we go to this load store instructions category. Okay. And software interrupt instruction, once SW is the opcode actually supported. Once that instruction is executed, to which mode the processor enters. It is supervisor mode. So we'll be discussing with one simple example, this is WI instruction. And the last is the program status register instruction. To affect, if you want to read the status of the condition flag, or if you want to write some data to the condition code flag register, how actually we can perform this using program status register instruction supported in ARM. So all those things we'll be discussing with examples. Okay. Coming to the data processing instructions, we in the previous slide we saw the instruction class of ARM. So first we had written data processing instructions. We shall go one by one. Okay. First we'll start with data processing instruction. Once it is completed, we'll look into branch instructions, and then we'll go to the load store instructions with single register transfer and multiple register transfer. Finally, we'll be ending up with software interrupt instruction and program status register instructions. So now we are starting with data processing instructions. So you know that data processing instructions, they manipulate the data which are held in the register. So data processing instructions cannot perform operations on memory. Operations are possible only on the registers. So which are the data processing instructions supported in ARM? So these are the instructions: move instruction, arithmetic instruction, logical instruction, comparison instruction, and multiplication instruction. That is multiply instructions. So under data processing instructions, these are the different instructions we will be discussing: move, arithmetic, logical, comparison, multiply. Okay. And you know that in all these data processing instructions, one of the one of the source register can be pre-processed using inline barrel shifter. So most of these data breaks, there are few exceptional cases which doesn't use barrel shifter operation, which cannot use or which will not use barrel shifter operation. But most of the data processing instructions, they can process one of their operand, one of the source operand using barrel shifter. Okay, this is one point you need to remember with respect to data processing instructions. So these are the data processing instructions supported: move, arithmetic, logical, comparison, and multiply. Okay, and in most of these data processing instructions, one of the source register can be pre-processed using barrel shifter. Okay, this is one point. Another point is, if you are using yes suffix in the data processing instruction, then it is going to update the flag in the CPSR register. The condition flags in the CPSR register will be updated. So these are the points you need to remember with respect to data processing instructions. And if you consider move and logical instructions, so these are the different instructions we have discussed. If you consider this move instruction and logical instructions, they are going to update these three flags: carry flag, negative flag, and zero flag. Okay. Remember, move, if it is asked to write the status of the flags, condition flags after execution of move or logical instruction, you need to look into only these three flags. NZCV are the four condition flags supported in ARM. But what you have to look, if it were to be move or logical instruction, just check the carry flag, negative flag, and zero flag. So only these flags will be affected with respect to move and logical instructions. So when actually carry flag will be set. So this is where This is how the carry flag gets affected. So the carry flag C is set from the result of barrel shift as the last bit shifted out. So what is the meaning of this statement? Assume you are performing the right shift operation. So whenever you are shifting the bits towards right, least significant bit will be lost. So that least significant bit status, whatever being shifted, that will appear in the carry flag. Okay. In the result, LSB bit will be lost, but the same status will be reflected in the carry flag. Or if you are performing left shift operation, you are shifting the bits towards left. In that case, MSB bit will be lost in the result, but the same MSB bit status will appear in the carry flag. So if you are using yes suffix in the instruction, okay, in the move instruction or logical instruction, so whenever you are performing the shift operation, left shift or right shift operation, so carry flag will be reflected with the MSB bit or the LSB bit. If you are shifting towards left, the MSB bit shifted will be appearing in the carry flag. If it were to be right shift, in that case, LSB bit status will be appearing in the carry flag. So this is how the carry flag gets affected whenever you are performing move instruction or move operation or logical operation. So with move or logical, if you are using barrel shifter, the carry flag will be affected when shift operation is performed towards left or towards right. Okay. Coming to the negative flag, this you already know. It is the MSB bit status, which is the sign bit status, which that is reflected in the negative flag. Okay, bit 31 of the result that is reflected in the negative flag. And coming to the Z flag, that is zero flag, it is set if the result is zero. So you have performed some data transfer. You have transferred some data to a register, and once the transfer takes place, if you see that the data held in the destination register is zero, then obviously zero flag gets set. Okay, or if you have performed some logical operation, and if the result of operation is zero, then zero flag gets set. Okay, 2 point. Now coming to the move instructions. So under data processing instructions, we are now discussing the move instruction. So this is the simplest ARM instruction supported. And what is the use of move instruction? You already know. Since we have already used several instructions, which includes move mnemonic, right? So this instruction is useful for setting initial values as well as for transferring the data between the registers. So if you want to initialize a register with some value, we are using move instruction. Another application of move instruction is for performing the data transfer between the registers. So content of one register you want to transfer to another register. So in that case, you can make use of move instruction, right? So the syntax for using the move instruction is like this. We are going to specify the opcode. Instruction means we are going to specify the opcode here. Followed by that, just observe, we are going to specify the condition attribute. After that, yes suffix, and next we'll specify rd comma rn. So whatever specified within parenthesis, this is optional in the instruction. So if you want to give the conditional attribute for this instruction, you can give it or you can skip it. Similarly, if you don't want to affect the flags after performing the operation, you can just skip yes. Yes suffix can be skipped. So whatever we have specified within pair of flower base, this is optional. So that's why in the syntax, this is how the format is written. First the opcode, then we'll specify the condition attribute, and if the instruction is to be executed based on the condition, you can add the condition attribute. And you've already seen the table which contains a list of condition attributes which you can use for this data processing instruction. Then yes suffix need to be used if you want to affect the flag. Then space. This complete thing will be the opcode. Instruction, condition, yes. So this includes the opcode. Space you are going to give, and then you'll specify the destination register, comma n. Okay. So what is the meaning of this? That is, it copies n. So since we are talking about move instruction, so this is the syntax we have discussed. What this instruction will do is it copies n to the destination register RD. This is what the operation performed by this syntax. But RD is the destination register. What is n or what can be n is, it can be either a register Rm or it can be an immediate value. Okay, so this is what n can be. Okay, coming to the two different move instructions supported. MOV is one of the opcode that is supported. MOV RD, RL. What is the meaning of this instruction? It copies n into the destination register RD, where n can be either a register RL or it can be an immediate value which is preceded by hash. Okay, so this is how you can explain the instruction. So once move RD, n instruction is exit. This is just the general syntax what we have written, not a specific example. Once this instruction is executed, what happens? It copies n, whatever the source we have specified, that is copied into the destination register RD. So here n can be an immediate value. You know how to represent an immediate value. We are going to prefix or precede that constant with hash. Or if it were to be a register, we'll specify the register. The source operand can be either a register or it can be an immediate data. Another opcode supported with respect to move instruction is MVN instruction. MVN RD, N. Okay. What actually the operation performed in this instruction is, this instruction copies not of n. MVN stands for move not. Okay. That is once complement of the source operand is taken and that is transferred to the destination register RD. So this is the operation performed. So that's what I've explained here. This instruction copies not of n into destination register RD, where n, there is a second operand what we have specified in the instruction. It can be either a register Rm or it can be an immediate value which is preceded by hash. Okay. And what is the important thing you have to note with respect to these move instructions? Only the destination operand is affected, but the source operand will be unaffected. So in any instruction you take, source operands will not be affected. Only the destination operands will be affected. Okay. So this is about move and MVN instruction. So now we shall look into few examples with respect to move and MVN instruction. Coming to the first example. Copy the contents of register R5 to register R7. So this is the precondition we have considered. R5 is loaded with the value 5 represented in hexadecimal. R7 is loaded with value say 8. So this is how the template we have used to give the example. Okay, precondition is this: R5 with 5 and R7 with value 8. And the instruction, you know what is the instruction you have to write to perform this operation. This is simple data transfer. That is, we need to transfer the content of R5 register to R7. This is the instruction you are going to write. Move R7, R5, where in this instruction R7 is the destination register and R5 is the source register. Now what will be the post condition? This is how you can specify the post condition. Will it affect R5 register? No. In this instruction, R5 is the source. You know, source operand will not be affected. So the content of R5 register will be as it is. It is 5 only. So before execution, whatever was the status on R5 register, same thing is retained in the R5 register. But R7 register, you can observe, previously it was having the value 8. Now it is changed to 5. So this is how you can specify the pre-condition and post-condition for the instruction. Okay, this template is being followed throughout your textbook for giving the examples. Okay, moving on to the next example. Copy the not of contents of register R5 to R7 register. So you can expect such questions in your internals or exam. They may give you a statement. To perform that operation, you may have to specify the sequence of instructions. It may be a single instruction or sequence of instructions you may have to write to perform that specified operation. They may give you explicitly which mnemonic to be used to perform the operation or which mnemonic should not be used to perform that operation. So read the question carefully. Accordingly, you have to choose the instruction to perform that specified operation. Okay. So such examples we'll be discussing. Here this is the operation specified. We shall consider the precondition as R5 equals 0x 5 and R7 with value 8. if you know the mnemonic supported to take the not of the source register content, it is MVN instruction, MVN R7, R5. If this instruction is executed with this status in R5 and R7 register, so what will be the post condition? You know, it is R5 is the source register, which will not be affected, whereas R7 register, so this will be the status. You can observe R5 content is taken, which is all zeros, 7 hex zeros, followed by that it is 5, 0, 1, 0, 1. If you just take one's complement of this data held in R5 register, you'll get that is most significant 7 hex digits will be F and least significant hex digit will be E. If you take 5, 0, 1, 0, 1, if you take the ones complement of it, it will be 1, 0, 1, 0, which is E. Okay, so this will be the result. Move on to the next question. Give the status of carry flag, zero flag, and negative flags after execution of the following instructions. Okay, this is the three condition given and the instruction. What instruction we'll see. Assume R1 register is having the value 2 and R2 register is having the value that is 8 followed by 7 zeros. And now the flag status is also given, since we have to guess the flag status after execution of the instruction. So what is the initial flag status? That is specified here. If it were to be written in lowercase letter, you know that the flag status is 0. Negative flag status is 0, zero flag status is 0, and as well as carry flag status is 0 here. And now the instruction executed is move yes R1, R2. How to explain this instruction? Move yes, you know. So R1 content of R2 register will be transferred to R1 register. Okay, R1 is the destination register, R2 is the source register. After the data transfer takes place, since yes suffix is given in the instruction, it is going to affect the condition code flag. And you know which are the condition code flags that gets affected if new instruction is executed. It is N, Z, and C flags. Overflow flag will not be affected when move instruction is executed. Move instruction with yes suffix. Remember, if you miss this yes suffix, it will not affect any of the flags. But if you are giving yes suffix, it will affect these three flags, C, Z, and N. So now can you tell what will be the effect after execution? What is the post condition they are going to get? Just see, will it affect R2 register? What will be the status of R2 register after execution of this? Hope you are following.
Not affected.
So R1 register will be loaded with the value whatever is in R2 register. So both R1 and R2 will be having the same data, 0x 8 followed by 70. What will be the status of flags? Which flag will be affected?
Negative flag will be
Yes,
set
very
to
good.
1.
Negative flag, since the MSB bit in the destination register. Just see the destination register R1 content. It is 8 followed by 7 zeros. 8 means 10000, where the MSB bit, the sign bit is 1, which is reflected in the negative flag. So the flag status will be, see, we have written this using this convention, capital N, ZC. Only negative flag will be set to 1. Okay. Coming to the next example, this is the precondition given. R0 is loaded with the value 50H, and this is the flag status given NZC. That is, each of these flags status is 0. Assume the instruction move S R0, hash 0. So we are trying to load 0 to R0 register. Based on this operation, we are trying to affect the flag since S suffix is given. And you know, R0 value will be changed now, since R0 is the destination register. In the post condition, we can specify R0. See, it is initialized with the value 0. And the status of the flag, since the destination register is having the value 0, Z flag will
Zero
be
flag
set
will be
to
set
1.
to 1.
Yes, very good. So just observe, negative flag and carry flag are not affected. Only Z flag is get set to 1. We are not using any barrel shifter operation in this move instruction. If we were to be using barrel shifter operation, in that case, based on the left or right shift, the carry flag would have been affected. But here what we are observing is, since the result of operation is 0 and the most significant bit in the result is also 0, we can observe negative flag status is 0, whereas 0 flag status is 1. Okay. Move on to the next example. Okay. This is the precondition. R naught is loaded with value 3. And this is the flag status. Okay, the NZC, and this is the instruction executed. Can anyone explain this instruction? What is the meaning of this? MOV NES R naught comma hash 0. Just recall the template what we had discussed. Opcode, condition attribute, then S suffix. So we can write complex opcode. So since in R we can have conditional executions. Okay. Can I explain the instruction and later on we shall see the effect?
Ma'am, it will move only when the zero flag is set to 1.
Check out. What is the condition attribute we have used?
Not equal condition, ma'am.
Will zero flag status, it gets executed if zero flag status is 1 or 0? Not equal.
Not equal to 0.
Uh, Not equal to 0? I think you are getting
Set flag
confused.
status will be 0, ma'am.
0,
It
right?
checks.
Not equal to 0. La. It should be 0. NE means see, this is a conditional execution instruction we have written. MOV is the actual operation to be performed. Just identify, try to split this instruction. MOV, that means simple move operation is to be performed. And what is the condition attribute we have used? It is any condition attribute. That means this instruction has to be executed only if zero flag status is 0. Any image, it checks the zero flag status in the condition flag field of the CPSR. If its status is 0, then only the move instruction will be executed. After execution of the move instruction, since S suffix is given, it is going to affect the N, Z and C flags. Okay, that will be affected. So this is how you have to explain. Move NES R naught comma hash 0. What is the execution effect? It checks the status of 0 flag. If 0 flag status is 0, then 0 is loaded to R naught register and the flags N, Z and C flags will be affected. So this is how you have to explain. And now we can see the initial status of NZC flag is 0. After execution, since Z flag status is 0 in our example, the instruction gets executed and R0 gets loaded with value 0. And what will be the flag status? We can observe Z flag is set to 1. Since result, the data held in the destination register is 0, now the 0 flag is set to 1. Okay. Moving on to the last example. This is the R0 register content, that is 0. R1 register is having the value 9 followed by 5034H. And this is the flag status. Z0 flag status is 1. Before execution of the instruction, what we are going to discuss, this is the flag status we are assuming. Negative flag is 0, 0 flag is 1 and carry flag is 0. And this is the instruction that is to be executed. Move EQS R0, R1. Now can you explain this instruction? Move EQS space R0, R1. When move instruction will be executed?
It checks
It
the
will
Z
execute
flag
when the
status.
Z flag is 1.
Yes, very good. When Z flag checks the Z flag status before executing move instruction, since it is conditional execution, it checks the Z flag status. If Z flag status is 1, then only move instruction will be executed. After move instruction is executed, it is going to affect the three flags C, Z, and N flag. Okay, and you can observe, since Z flag is 1, this is the initial status. Z flag is 1, condition is satisfied. So R1 content gets transferred to R0 register. Now R0 value will be changed. Our previous R0 value was 0. Now R0 value will be 9 followed by 5034H. Okay, and R1 register, since it is a source operand, its content will not be altered, but the flag status, if you just check the flag status, since it is 91001, you can observe negative flag is set to 1. It is reflecting the sign bit in the destination register. N flag is set to 1, and the result of operation is not 0. R0 is not having the value 0, that's why 0 flag status will be now 0. Prior to the move EQS instruction execution, Z flag status was 1. Now, since S suffix we have given, after execution of this instruction, you can observe Z flag status is changed to 0. So it is written in lowercase. And carry flag status, it remains as it is. So that is, it is 0. The status is 0. Okay, this is how you have to explain the instruction. So you may be given with a problem, say they may give you the precondition and the instruction. They may ask you to explain that instruction as well as what is the result or effect of execution of that instruction. You need to explain it properly, and you have to give the post conditions, that is after execution of the instruction. Okay. Hope these examples are clear. Moving on to the next topic. As you know that the syntax of move instruction we have already seen. Okay, move rd comma n. So thus in this, the source operand what we have written n, what I told in the previous two instructions, what we discussed, mov opcode we have discussed and mvn opcode we have discussed. In these two instructions, the format is mov rd comma n or mvn rd comma n, where rd is the destination register and n. So what can be n? Well, we have discussed n can be either an immediate data which is preceded by hash symbol, or it can be a register rm. Okay, but in addition to this, so this is what the normal instructions we are going to write. But you know, ARM important feature supported in ARM, that is barrel shifter. In addition to this, either taking n as a register or immediate value, we can pre-process the source register content using inline barrel shifter. Okay, this is the additional feature supported. So that's what is specified in this point. N can be a register RM that has been pre-processed by the barrel shifter prior to being used by a data processing instruction. So you can just make the instruction bit complex by adding barrel shifter operation to the data processing instruction. So this is the diagram which shows the data flow between the ALU, arithmetic logic unit, and the barrel shifter. So in the program flow model of ARM, we have seen this. The same thing is copied here. Okay. If it is asked to explain the barrel shifter operation with this neat diagram, you have to explain where you are seeing the data flow between this arithmetic logic unit and the barrel shifter. So directly we can take the operands, and on that you can perform the arithmetic or logical operations, which includes ALU component, or one of the source register Rn. You can see Rn register is not pre-processed. Rn register is fed to ALU directly, whereas Rm register content, it is given as input to the barrel shifter, which does some pre-processing. Either the 32-bit data held in the Rm register can be either left shifted by some shift amount, or it can be right shifted by some shift amount. The result of that barrel shifter is given as input to the ALU. So this is called as pre-processing. Using this hardware component, barrel shifter, so the RM register content is pre-processed. That is, one of the source register content is pre-processed. That pre-processed data is being used in the data processing instruction. So after the operation is performed, the result is stored in the destination register RD. Okay, so this is the barrel shifter operation. So that's what being explained here. Okay. A few points to be remembered with respect to barrel shifter. The data processing instructions are processed within the arithmetic logic unit. The important feature or the powerful feature that is supported in ARM is the ability to shift the 32-bit binary pattern, 32-bit data, since the RM register what we are taking is 32-bit. In one of the source register, it can be left shifted or right shifted by specific number of positions before it enters the ALU. So this will increase the power and flexibility of many data processing operations. And one more important point is this pre-processing or shift, it occurs within a cycle time of the instruction. So within one cycle, this pre-processing takes place as well as the data processing operation takes place. Okay, so this will be useful. That is, this barrel shifter operation will be useful for loading the constants into registers as well as for achieving fast multiply or division by power of 2. So remember, there is no division instruction in ARM. Multiplication instructions are supported. If you, instead of using separate multiply instruction, in powers of 2, if you want to perform the multiplication operation, or in powers of 2 the division operation is to be performed, that can be performed using this barrel shifter operation within the data processing instruction itself. So this improves the speed of execution. So one instruction can perform more processing operation. Okay, this is the advantage. Okay, this time up. Let us stop here, since the next slide it requires more points to be discussed. One more important thing I wanted to tell is there are few instructions in ARM that doesn't use barrel shifter. Say for example, multiplication instruction, mul instruction is there, and one more instruction, qadd instruction is there, and clz instruction. So these are few instructions which doesn't use barrel shifter operation. In multiplication instructions, we cannot use barrel shifter operation. So there is CLZ instruction, counting leading zeros. What is that instruction and what is the effect of execution of the instruction? We'll see with examples. So few example instructions that doesn't use barrel shifter are mul, mul is the opcode, CLZ is another opcode, and qadd. So the saturated addition with respect to I told qubit. If the ARM is supporting that is enhanced DSP instructions, in that case qadd instruction if you are using, uh, those instructions will not make use of barrel shifter. It is not supported with respect to these instructions. Okay, so what are the barrel shifter operations supported in ARM, and what is the execution effect after that barrel shifter operation is used in your instruction? With examples, we are going to discuss in the coming class.